Thanks for the introduction. Hi, my name is Feng, and today I'm going to talk about our work, Lumina, real-time neural rendering by exploiting computational redundancy. This is a joint work between Shanghai Jiao Tong University, Shanghai Qizhi Institute, and University of Rochester. So let's begin. Rendering photorealistic scenes using conventional ray tracing is challenging. It requires meticulous modeling of lighting, geometry, and more. 3D Gaussian splatting avoids such hassles and rendering 3D scenes through a set of Gaussian points using an autoregressive training process. And using such representations, 3D-GS has been widely used in many applications, as I show here. Now, given a set of Gaussian points, how should we render a scene? Overall, 3D-GS algorithms renders an image tile by tile, and it consists of 3 key steps: projection, sorting, and splatting. The first step, projection, is to project each Gaussian point onto the rendering canvas and check which tile is intersect with this rendering canvas. Once we finish the Gaussian tile intersection, we need to render them in correct order. So the next step is to sort Gaussians tile by tile from the nearest to the farthest. Lastly, we need to integrate those Gaussians one by one to obtain the pixel value. However, if we look at the 3D Gaussian performance on off-the-shelf GPUs, we will see that the workstation GPUs can achieve real-time performance, but is too power-hungry. On the other hand, mobile GPUs are more energy efficient, but cannot achieve real-time performance. So our wishful thinking is to achieve real-time performance with an extremely low power budget, which is required for AR and VR. So to do that, let's first understand where the performance bottlenecks are in 3D-GS. Here we show the model size of different datasets. We find that the model size or the number of Gaussians increases with the complexity of the scene. More points means more computation. Especially for real-world scenarios, their model sizes are order of magnitude higher than the synthetic ones. So the first point is that model size increased with the complexity of the scene. Next, let's measure the performance of 3D-GS on a NVIDIA Xavier SoC, which has roughly the same computation capability as recent VR chips, Snapdragon RX2. We show that 3D-GS algorithms cannot achieve real-time performance, especially for real-world scenarios. This also motivated us to accelerate 3D-GS algorithms. Lastly, we profile the execution of 3D-GS algorithms on various workloads. We find that although the rendering latency varies, the execution bottleneck does not shift as the model size increases. The main computation bottleneck remains rasterization. So to summarize, the overall computation of 3D-GS is heavy and it cannot achieve real-time performance on mobile devices. And most importantly, the main computation bottleneck is rasterization. So based on our characterization, we will first talk about how to reduce the computation by using our radius caching techniques. However, once we apply radius caching on 3D-GS, we will inevitably introduce warp divergence on GPU. So we address warp divergence or workload imbalance across threads via our algorithm and hardware co-design. Lastly, we show our evaluation. So let's talk about the radius caching. There are numerous studies on efficient 3D-GS recently. If you allow me to use one sentence to summarize the core idea of this work, that is to reduce the number of Gaussians in the model size, in the 3D-GS models. Because less Gaussians means less computation. However, if we wonder if there are any other solutions to reduce the computation. For example, how about tracing the light path? And before I explain our idea, let's first recall how to determine a RGB value of a pixel in 3D-GS. So as the equation I show here, the pixel value is determined by the integration of intersect Gaussians from the nearest to the farthest. So in primary school, we know that any two distinct points in 3D space determine a line. If these two arrays intersect the same set of Gaussians in the same order, we can think these two arrays have the same direction. So we can safely approximate the RGB value of one ray using the other. In addition, we find that if we want to approximate using one ray to approximate the other, these two rays does not have to share exactly the same set of Gaussians. What we need is to let them to share the initial set of Gaussians, we call them prefix Gaussians. And if they share the same set of prefix Gaussians, their final colors are similar. And naturally, we can cache the rendered pixel results by using prefix Gaussians as a key and RGB colors as a value. However, there's one catch. On average, each ray would intersect with thousands of Gaussian points. Even we store, for instance, hundreds of points, that will pose a significant on-chip storage overhead. To address this issue, we find that across different scenarios, 1.5% of Gaussians determines 99% of RGB values on average. So this means that we don't have to store all prefix Gaussians. Instead, what we need is to use significant Gaussians on prefix list instead of all Gaussian points. This way, we can keep the cache key much smaller. Now, let me explain our radius caching idea. So for the very first frame, we perform normal rasterization to obtain pixel value. Then for each pixel, we determine the significant prefix Gaussian IDs. For instance, for pixel 1, the significant prefix Gaussian is 5 and 16. And then we concatenate these two Gaussian IDs and store them as a tag in the radius cache. And the corresponding RGB colors is the cache value. Similarly, we populate the radius cache by inserting the remaining pixels. Next, let's see how radius cache can accelerate the remaining frames. So we first perform the rasterization for the Gaussians in the prefix list. Once we finish the computation for this part, we identify the significant Gaussians in the prefix list and use them as a cache tag. For example, the tag of pixel 2 is 18. Next, we query the radius cache using these tags. In this example, pixel 2, 3, 4 have the cache hit, so we can directly use the previous cache results as their rendering results. So we can save the computation for those pixels. And for the remaining pixels, in this case, pixel 1, we still have to finish the remaining computation, and then we update the radius cache. So that's how we use radius cache to accelerate rasterization. Now let's see the results. So here, the x-axis shows different datasets, and the y-axis shows the quality metrics, PSNR. Overall, radius cache can achieve 76% of pixel savings with minimal accuracy loss. Next, let's see the performance comparison. Again, the x-axis shows different datasets, and the y-axis shows the speed up. We first show the baseline. Then we show the results by directly implementing our idea on mobile GPU. The result shows that even we can reduce the overall computation, but we show no speed up. And actually, we show some performance degradation. And you might wonder, why is that? And in the second part of my talk, I will explain the performance, why there's a performance degradation and how we address it. Now, let's first recap the color integration process in rasterization. In this process, we render pixels tile by tile. For instance, if we render the first tile T0, each Gaussian in this Gaussian list would calculate intersect transparency alpha with all pixels. For each pixel, if the alpha is greater than a threshold, we will perform the color integration process. Otherwise, we will skip the color integration process for this particular Gaussian. And the final pixel value is the integration of all Gaussians in this tile list. If we consider a GPU warp with 4 threads, and these 4 threads are integrating Gaussian, for instance, when these 4 threads integration Gaussian 1, all threads would perform alpha computation. However, only thread 1 and 3 would perform the remaining color integration because their alpha is greater than the threshold. And threads 0 and 2 would do nothing because they are masked by the GPU. Similarly, when integrating Gaussian B, thread 1 is masked by GPU, and as we can see, the warp divergence already exists in the existing rasterization process. Now, if we consider using radius cache, some of the color integration process will be skipped. For instance, the red crosses highlight the parts that can be skipped using our radius caching, and in this case, the overall execution latency is still bounded by the critical path, which is a thread that cannot be skipped using our radius cache. Applying radius cache, that's why applying radius cache would make warp divergence even more severe, and we design a specialized accelerators for that. So in previous 3D Accelerator design, each process unit is responsible for one pixel and integrate Gaussians one by one. Here we show the PE design for alpha computation and color integration. Due to the warp divergence, as I explained in the previous slides, we know that PE utilization of alpha computation is high and the utilization of color integration unit is low. And to address this issue, we let multiple alpha compute units connect with one single color integration unit via a FIFO, so that the single color integration unit would work on multiple pixels. And this design has two modes. One is to render multiple pixels in parallel, and the other is to let multiple alpha compute units to co-render a single pixel. Meanwhile, we also extend the backend color integration unit with our hardware radius cache. So there are some more details in our paper. Please see our paper for more details. And here's our overall architecture design. So on our SoC, we execute rasterization on Lumina core, and the remaining operations are executed on GPU. Lastly, we show our evaluation. So in our evaluation, we implement a 8x8 rendering core with an on-chip global buffer with a dedicated radius cache. In our evaluation, we have three hardware baselines. The first one is GPU baseline. The second one is GPU with software radius caching. And last one is our architecture design. Previously, we showed that we achieve no performance gain with software implementation of radius cache. And here we show that with dedicated accelerator design, we can achieve 2.5 times speed up against the GPU baseline. And by incorporating with dedicated ASIC GS core, we can achieve 16 times speed up against GPU. And there's some more results in our paper. So to summarize, 3D GS is a new photorealistic rendering pipeline, and we propose a new technique, radius caching, to reduce the overall computation. However, introduced radius caching will inevitably introduce irregular color integration in 3D GS, which leads to low utilization of the GPU on GPU. So we designed a dedicated accelerators to address this issue. And lastly, our algorithm hardware co-design can achieve 2.5 times speed up, and with some more optimizations in our paper, which I didn't mention in this talk, we will altogether can achieve 4.5 times speed up. And that will be the end of my talk, and I'm happy to answer any questions.